I want to start with asking you a question. Did you ever feel like you want to be at two places at the same time? Yes, me too. I mean, I strongly remember not so long time ago when the kids were not so big, and I really wanted to finish work late, and I really wanted to pick up my kids early from kindergarten. So, well, it's a simple rule of life. We can only be in one place at the same time, so you have to choose. However, what I'm talking about today is that although that's a natural law for us humans, it's not the case for the particles that form our body. So it's not the case for the neutrons, protons, and electrons that we are made of. Okay, so before coming there, I want to take a small detour around my own childhood. So this is something that my father worked on when I was born, and when I grew up, I wanted to talk to my father, and he is an engineer, and he doesn't like to talk about emotions and feelings and stuff like that. So I figured out if I talk about motors, yes, then we can relate. So he told me all about how this big ship engine works, how there's an explosion in the cylinder. The cylinder is so large you can even stand in it. And that makes the piston go down. The piston pushes on the propeller shaft. The propeller shaft makes the propeller go round, and that pushes water backwards, and the ship goes forwards. Wonderful. I as a kid, I really had the feeling I can understand this. I can understand how this works. And we also used to watch these popular science shows together. Like when I was a kid, it was Cosmos with Carl Sagan. Now I guess it's Cosmos with someone else. You really had the feeling that you could understand how the universe was formed and evolved, and how the world works. So this made me want to become an engineering physics guy. So I started studying engineering physics, and it all went well. So first year, second year, then in the third year, I was truly shocked. So in the third year, we had this class of quantum physics. And there, the lecturer talked about electrons. And I guess most of you are old enough so that you have seen this old television screen, right? So the screen is there, and then you have electrons there. You accelerate them towards the screen, and they hit. Now it's much flatter, I know. So, but then the old ones, you hit, and each electron hits the screen in one point, and makes a colorful dot that forms the pictures that makes the movie. And each electron hits in one spot. So each electron is in one place when it hits the screen. Fine. So this part I could understand. I could relate to that. But when the lecturer then went on and said that, well, that's not the full truth. It's actually like if you send electrons from here onto two openings, they will proceed towards the screen, and they will interfere like waves, like light waves or water waves, and produce an interference pattern. Okay, I could handle that as well. I mean, many electrons, they interfere with each other, should work. But then came the really strange thing. The lecturer said, the lecturer said that if you reduce the amount of electrons so they come one by one, you still, in the end, get the same interference pattern. What? I mean, so the electrons, each electron goes through both slits, and then hits in one point. So it's a point-like particle, but it goes through both holes. I got so shocked that I sort of got stuck on this, and I worked on quantum physics almost since then. And I think for me, the best way of conveying, I mean, if you're not astonished, I have this cartoon here, which try to convey this message. So electrons routinely does this. They go on both sides of an obstacle, while we humans, we are in one place. So, yes. And this peculiarity and counterintuitiveness of quantum physics has been known already since quantum physics was discovered in the early 20th century, but this counterintuitive aspect of single electrons and single quantum objects has not been explored too much until quite recently. So there are two gentlemen here who pioneered this work, working with single atoms and single photons. So that's David Wineland and Serge Haroche, who shared the Nobel Prize in physics in 2012. So it's quite recently that science and technology evolved so that can handle routinely single quantum objects. Okay. So nature is counterintuitive, but as an engineer, I have to ask the question, can we use it for something, this counterintuitive aspect? Well, if for computers, if you go down into the memories and where you store all the pictures and movies you have in your phones and so on, they are stored in large quantities of bits. So in each memory position you have a 0 or 1. Okay, so if we now make this into a quantum bit, where we can store both 0 and 1, you know, left and right, 0 and 1 at the same time, what will be different? Well, if you have one qubit, one quantum bit, it can store 2 possibilities, while a classical bit can store only 1. So it's twice as good, right? Okay, that's good. And then if you take 2 qubits, it can store 2 times 2, that's 4 times as much. It's getting better. And, well, then it doubles for each new qubit, and that basically connects to the story about the man who invented chess. And the emperor said, "Oh, this is such a great thing. I want to reward you with something. You can wish for whatever you like." And this man said, "I'm a humble man. I just want 1 grain of rice on the first square. And then I take 2 on the next one. And 4 on the third, and double it like that." And, well, the emperor said, "I have lots of rice, no problem." What he didn't calculate was that on the 64th square, you have to put 1,000 times more rice than we produce in the whole world today. So the emperor, according to the story, was a little bit not so happy and, chopped the head off. Well, if you now come back to qubits. So somewhere on the 50 square or so, this exponential growth, this capability of qubits to keep many possibilities at the same time goes a little bit crazy. So if you have 60 qubits or more, there is no way, even with today's best classical supercomputer, you can simulate what's happening. So a quantum computer with 60 qubits or more will do something that we don't know exactly what it will be. So I think all of this sounds a little bit abstract, right? A little bit. So here, in my hand, I have a 3-qubit chip produced by my experimental colleagues at Chalmers. And they are aiming now for 50 qubits in a few years. There are groups in the world producing different sizes of chips, and you can even log into a cloud service called Quantum Cloud, where you can play with your own 20-qubit quantum computer. So not 60 yet, not this amazingly large amount, but they exist. So I'm really fascinated about this, and I'm wondering what you can do with it. So my experimentalist friends try to build it. I'm trying to figure out what we should do with it. So the first guy who figured out something very practical to do with a quantum computer is this guy, Peter Shor. So in 1994, he discovered that on a quantum computer you can solve the following problem. Well, if I give you two numbers and I ask you to multiply them together, you can all do that. If you don't do it in your head, you pick out your pocket calculator, straightforward. However, if I give you the big number and ask which two numbers did I multiply, that's a hard problem. Actually, there is no better known way than to search through the reasonably sized numbers. And that, if you take a very large number, that takes forever, even on a supercomputer. And the fact that this is a hard problem is the basis for the security on the internet. When you connect to your bank through HTTPS, to break that code you're using is the same thing as finding these two numbers. And that's hard. And it's hard as long as you don't have a quantum computer. So if you build a quantum computer large enough, it will break the codes. Okay, so how does the quantum computer do this? I think that's kind of interesting. So Peter Shor explored, so even if you don't know much math, you can see that this formula here is a function of x. It's quite small. It involves this large number n that you want to find the factors of. And if you plot this function, which I did here, you see that it looks like noise. But it has a period. So it looks like noise, but then it comes back exactly the same. If you find this period, you have found one of these factors and cracked the code. So why don't you do this on a classical supercomputer? Well, the x-axis is simply too long. It's from 1 to up to the big number n. You don't have the time and the power to calculate all that. But the quantum computer can do that. It can calculate all the values of the function simultaneously for all these x values. And you only need as many big quantum bits as you need to represent this big number n. And not only that, Peter Shor realized that you can also do a so-called quantum Fourier transform, and you can find the period and read it out. So a funny thing with quantum bits is that when you read them out, all these vast possibilities collapse into one. And then you want to make sure that it collapses into the answer to the problem. So you want to have problems which you can formulate compactly, that then explores many, many possibilities and collapses to a small answer. Not all problems are like that. So, and we are currently exploring what more things you can do on a quantum computer, because frankly speaking, I didn't become a scientist to crack codes. It's fun, but I think it would be much more interesting to do something a little bit more useful. Well, I have a friend who is interested in this. It's the Titan, a moon of Saturn. There you have had space probes looking for found chemistry there. And this looks a little bit like biological molecules here on Earth, but they are a little bit different. So there's no oxygen, so they are hydrogen cyanide based things. And a question is this can life grow from this? Well, I mean, you could try to do the experiments, but my friend tells me that would take thousands of years because the processes are slow. So he explores this in computers. And there, because it's quantum objects, when these chains grow, the processor power of today's supercomputer dies. And I'm quite convinced that the quantum computer will help him. And I think that's a quite cute problem. But there are more practical problems. So here you see most of the flights that occur on the world for a day. And what airliners do is they have to optimize these flights. They have to find which plane should go from here to there, And for each plane, they should find a crew, and all this should fulfill all the requirements for the crews to sleep, and everything that they should do. And this airlines do all the time. And this is a huge optimization problem. So we are talking to people working on this, and they said, so they asked us to, just calculate how many options there are if you start with trying to put 100 crews on 100 planes. So on the first plane, you can pick any one, so you have 100 choices. Then you have 99 choices for the next, and 98, and so on. If you multiply this together, it's this number. It looks big, right? So it's actually roughly the number of particles in the universe, 10 to 80 squared. It's a really huge number. You could never ever optimize this fully, right? And what we're exploring now is do this better than a classical computer. So maybe we can use these contra-intuitive aspects of nature to reduce fuel consumption of airlines. I find that quite amazing. Also, if you think about the future of self-driving vehicles, where you want to route vehicles so that you avoid traffic jams, that's a huge optimization problem. Maybe a quantum computer can help. This is quite interesting. And I would like you to think about other types of these optimization problems. I can give you just an example in your private life. If you ever gotten married or think about getting married, and you think about having 100 guests, and how many possibilities do you think you have to seat them? Well, the answer is written there, right? So, with this, I want you to think about how we can use this contra-intuitive aspect of nature to make society better. Thank you.